Mrs. Patel Dame here for topic 8.6, the molecular structure of acids and bases. So our first question here is figuring out what is electronegativity. So electronegativity, we've abbreviated that as EN. So electronegativity is the attraction between the electron of one element, the valence electron of one element, to the nucleus of another atom. Or we can say the attraction of a nucleus of one atom to the valence electron of another atom. And if we recall, the most electronegative element out there is fluorine, and the least electronegative is francium. So as you go across in the periodic table, the electronegativity increases, and as you go down in the periodic table, the electronegativity decreases. Some places to find values for this would be Table S of the New York State Reference Table. So a polar bond. A polar bond is when we have an uneven distribution of electrons between two atoms. So for example, if I have H and F, I believe the electronegativity value for H is 2.2. The electronegativity value for fluorine is 4.0. And we can always double check that with the New York State reference table just to double check to make sure that's accurate. So when we subtract the two, 4.0 minus 2.2, oopsies, double checking this for you guys, gives us 1.8. So we can say here that the fluorine has a greater attraction to those electrons. So I might show like a little arrow here and a positive charge on the tail. So showing that the hydrogen is partially positive and the fluorine is partially negative. So this indicates that we have a polar bond. These were all going to be dealing with covalent bonds as well. So it's a polar covalent or non-polar covalent. In terms of the difference between polar versus non-polar, and let's recall that if we have our electronegativity scale, it goes from 0 to, let's say, 4.0, 0 to 0.5-ish, that's going to be non-polar, so label that as non-polar. For the AP exam, 2.0 is our cutoff for polar. So 0.5 to 2.0 is polar. So again, make sure you label this. 0 to 0.5 is nonpolar. 0.5 to 2.0 is polar, and both of those are covalent bonds. Anything above that difference in electronegativity, we tend to talk about it as being more ionic. So something that has an electronegativity difference closer to 2 is going to be less ionic than something that has an electronegativity difference of like 3.7. So again, make sure you label this part as ionic, this part is covalent, we've got nonpolar, and then polar. And again, all of this is dealing with the difference in electronegativity. So if we subtract the two values, we end up getting those. We're going to be doing a worksheet. If you haven't already done it, make sure you take care of it. But some things I want to talk about with the worksheet itself is that they have some sections on there where you might see like a bar like that. And let's say you see some shading with it in that bar. So if the shading is even, and I'm going to kind of do this a little bit lighter. Yeah, I see that that's a bit of a lighter shade. If I had my better colored pencils, it'd be easier. But essentially what we're seeing is these shadings are showing us the difference in electronegativity or the electron distribution. So this is showing us an even distribution of electrons. And so this would be something that's nonpolar. So it's not like one is hogging the electron. So this might be between something like H and H. So this is their way of showing a bond. You might have something else where you have that bar and then lighter shading on one side, and then it gradually becomes darker. So hopefully you can see that. If not, let me lighten this up a bit. And you kind of see some faint shading in here. So this is showing us we have an uneven distribution of charge or uneven distribution of electrons. So this one tends to be polar. We'll find that the more electronegative one is over here, and that's partially negative, the partially positive has less shading or less electron density around it. So again, this one is polar. This area has higher amounts of larger electronegativity value. This has a lower electronegativity value. So hopefully, ideally, you've done this little POGO worksheet. And when I say POGO worksheet, I mean this one that deals with strength of acids. So some major points that we would talk about: the shorter the bond, the greater its strength can be. So the shorter the bond, the greater its strength. So it's going to take way more energy in order for it to deprotonate. So it's going to be less likely to deprotonate. And remember, when we're talking about deprotonating, we're just talking about, or protonating, we're talking about just a hydrogen atom, or ion, excuse me, hydrogen ion. This then leads to a smaller Ka, and therefore this will be a weak acid. And then the other major point, and you might have a few more. Great, awesome. These are just the two that I want to make sure that we get in here. We'll say the more polar the central atom is, or sorry, I would say, yeah. So the more polar between, let's see, the central atom is to H. We call that that hydrogen atom is going to be able to leave and deprotonate. And if it's going to be able to leave more easily, we're going to say that it's a strong acid. And I know that sounds so counterintuitive. We'll go with it. Just think about it. The terminology itself doesn't necessarily make sense, but hopefully you get the concept that the more polar that central atom is to H, meaning that if you have that central atom, which is a really decently strong, so strong electronegativity, you're going to see that it's going to have a stronger acids to be able to deprotonate that better. All right, and then this last little part over here, we're going to draw some Lewis dot structures for these three acids. So we have phosphoric acid, which is H3PO4. Then it's a so this is a triprotic acid, meaning it has 3 hydrogens. Then a phosphorus acid is going to be H3PO3, and a hydrophosphorus acid is H3PO2. Oopsies. So we can see that we end up having more oxygens in one versus the other. So if we look at the Lewis dot structure for each of these, we're thinking about what the central atom is. This one, phosphorus, will be there. We also say that they all have a double bonded oxygen. So I'm going to go ahead and take care of that double bonded oxygen, each one of these. Let's say I throw it up here at the top. And then this one has 3 more remaining oxygens and 3 more remaining hydrogens. So I'll show oxygen, 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 and then oxygen needs 2 bonds, so I'll show them as hydrogens, or attached to hydrogens. Note that would be a bent structure normally. This is not a perfect model, and no model is perfect. With phosphorus acid, we have 2 more oxygens left over, and I believe we have 3 hydrogens. So we have those 3 hydrogens, and then those are attached right there. And then phosphorus acid, we have 1 more oxygen, but we still have those 3 hydrogens, so one will be the OH, the other 2 will just be H's. So then we're going to rank them in terms of their acidity. So if we think about what can be removed, these hydrogens are a lot less electronegative than those oxygens. So they're likely to be a very polar bond. And so therefore, those could actually deprotonate pretty easily. Oh, sorry, one thing I forgot. This wanted a Lewis structure. So I need to make sure I show all the appropriate valence electrons on these. So give me a moment while I finish this and make sure that you put your total of 8 valence electrons around the oxygen, but we have 2 lone pairs. Cool. Awesome. And then over here with phosphorus acid, again, we have the OH over here. Those hydrogens are going to have a very different electronegativity value than oxygen. The oxygen is going to snap or hang on to those electrons more so. As opposed to hydrogen and phosphorus, they're somewhat more even. And then phosphorus acid will do the same thing over here to show that we have those as dipoles. So when we're thinking about which one's going to be more acidic versus less acidic, we have to think about which one's going to deprotonate more easily. And so we'll have you guys rank those, and we can take a look at their Ka values to kind of help us out with that. So the Ka values, you can Google them. I just happen to have my textbook nearby. Remember that old thing? And I'm on page A10 and A11 of our textbook. So for phosphoric acid, I can see that it has 3 Ka values. And it has 3 Ka values because it's got 3 hydrogens that were attached to those oxygens that can easily be picked off. So this would tell you how much the Ka is for the first hydrogen being removed from that first oxygen. This one's telling you the second one, and then this one's telling you the third one. So right now, I just want to take a look at the first Ka. So that is going to be 7.5 times 10 to the negative 3. Phosphorus acid, well, we have 2 hydrogens that can be removed. So therefore, there's going to be 2 Ka values listed there for phosphorus acid. And this one's going to be 5 times 10 to the negative 2, I believe. And then the hypophosphorus. The hypophosphorus, it has only 1 hydrogen in which it's going to be attached to an oxygen, so that one will end up being removed. And I don't think I have that value readily available. Hopefully you can find it for yourself. And then let me know what those are. But if you take a look here, we see that this one is a much smaller value than the phosphorus acid. So that'll help you out with when it comes to C. And then in terms of D, in terms of molecular structure, explain why one is more acidic than others. Consider its Ka value, and consider how many oxygens it's attached to, and then the attachment of those oxygens to those hydrogens. Might be a little vague. I'm sorry, we can explain it a little bit more, but I do want you to think about it before I give you all of those answers. So hopefully we'll get the chance to talk about that. And if you have any questions, let me know. Take care.